Okay, so this is the a new seminar on neurosymbolic artificial intelligence. And I shall try and define what is this topic and what all material we might cover. I'm going to begin by asking you a few questions. I have a few books on my desk here. Is anyone familiar with this book? Raise your
Yes,
hand.
sir.
Ah,
Yes.
there you have it. Raise your hand if you're familiar with this book. I'm
I
seeing you
also
on
have
video.
this book.
What is that?
I also have this book
You have
with
this
me.
book. Okay,
Mhm.
Archita, you have this book. Okay. All right. How about this one? Do you have this book?
I don't have this one.
You don't have this book? This is probabilistic graphical models. I've taught from this book for the last, I don't know, 7, 8 years. The book is about 7 or 8 years old ever since it came out by Daphne Kohler of Stanford. So I've been teaching out of that book. And how many of you are familiar with this one? Right.
Yes, yes, I
Uh,
think this is, yes.
Yeah. So this one is Thinking Fast and Slow
mhm.
by Daniel Kahneman. And what it says below his below his name, it says winner of the Nobel Prize in Economics, right? Winner of the Nobel Prize in Economics. So we're going to talk about this guy. He's not a computer science guy. He's a psychology, cognitive science, and what the Nobel Prize in Economics. And it turns out he is relevant to neurosymbolic AI in some way. So what we are going to be doing is these three books, right? And they are all substantial books. This book on deep learning is roughly how many pages? Last page is 775 pages. This book, and I've become quite familiar with almost all the 775 pages because I've taught from this book, maybe about 5 times in a row or something like that. What I've done is to cover all the material. Each time you cannot cover all of it; it's too much. So I cover like, some of it in the beginning and then jump into a few others. And the next time I teach it, some of it in the beginning and jump to some more chapters like that. I've been able to cover this book over the last 5 years. And this book, Probabilistic Graphical Models, is almost twice the size of the deep learning book. If I turn to the last page, this one is 1,220 pages. 1,220 pages book. Okay, see how thick it is? It's all fine print. It's all fine print and a lot of math and so on. Uh, I've become somewhat quite familiar with most of this book. I think I've read maybe except for a couple of chapters. So this is a book which was introduced about 8, 10 years ago. So I've also taught from 7, 8 years from this book. So I've become quite familiar with that one. This one is also new to me, but the basic ideas. Okay, now how big is this one? Daniel Kahneman's book is 500 pages long, and it's not math. It's mostly social writing. It's like psychology and that kind of stuff. It's very interesting about how the brain works and all that. And there are a few diagrams also. I'm kind of this much way in the book. I try to read a few pages. Pretty heavy duty reading, but so we could say, well, do I have to read all this material, which is about 2,000 pages, and a lot of it is math and equations and so on. Ideally you would you would absorb the main points in all of these books to go towards where we want to go. Of course, you can say, well, instead of reading the books, can I just read some papers? Yeah, you can do that also. And the papers, some of the papers I think all of you are registered participants in this course. I think if not, just send me your name and I'll add you to UB Learns. So if you go to UB Learns in the course information section, I keep on adding papers saying, let's read this paper. So what I want you all to do is, hey, there is some new stuff that's come out, and we should be doing this in neurosymbolic AI. Particularly, they're coming in the NLP area, natural language processing area, and say, let's cover that. So I'm looking for populating this whole area, and so that I welcome. So, but anyway, take a look at some of the papers, and these are all the books, and there's no chance you can read all of this material in one semester. But what I'm trying to do is pull in all the central material that I think is interesting and formulate a theory around it. So those are three books I wanted to begin with. And then I wanted to ask you about how you would go about solving one problem, either using neural networks or using symbolic methods to solve a given problem, and then think about what the solutions are like, and we'll do that. And then immediately that's going to suggest a small project in neurosymbolic AI for you, in both, also in thinking fast and thinking slow. And so you could try that out. Now, what are the requirements of the participants in the seminar? Is that I want you to take on something that really interests you as we're going along, and say, okay, you might stumble upon some material, like it could be a very current paper because people are beginning to think about this area. This is what happens in research. Deep learning was like that. About 5-6 years ago, it was not even a well-developed topic, and people started writing papers, and then suddenly it blossomed into an entire field. Neurosymbolic AI is probably there in the beginning points. And so there are papers coming out now, fast and furious, not that many still. And so you might say, this looks really interesting to me. And you bring that in and saying, okay, I'm going to jump in on this one topic and do something on it. Say it could be a presentation you do on it, and ideally you'd have a write-up on it also saying, this is what I did. So you could turn it into a class paper or something like that. Or it could be something you will implement, a small thing, and share with us what that means. And the second lecture, I don't know how much we're going to finish today, but I'll try and cover 1.1. If we finish 1.1, 1.2 is about research topics in neurosymbolic AI, where I'll call upon you to pick up one of those 10 topics in 1.2 and see whether you can make some contribution. And today itself, I'll suggest a small project that could actually become the basis for a new paper. I think it'll be quite revolutionary if you do what I'm going to suggest doing. All right. Okay, let's begin. Okay, now let's see course organization. Are there any questions about what we're going to study? Okay, if not, so let's continue. So to introduce this neurosymbolic AI, as you can get a sense, the neuro is the deep learning part. Symbolic is something like probabilistic graphical models. That's why I mentioned those two books. And then I mentioned thinking fast, thinking slow. You can imagine thinking fast is about deep learning. Thinking slow is about, causal reasoning and conventional symbolic methods and so on. So that's how to put these two together and how they are put together in our human brain, right? So that's the kind of thing. Anyway, let's think about a simple problem. This is something I've introduced in the past. Maybe those of you who took Introduction to Machine Learning with me a couple of years ago, I think I gave as project one fizz-buzz, right? The problem of fizz-buzz. Anyone remember what fizz-buzz is? The fizz-buzz problem? No? No volunteers? Say yes, I know. No? Fizz-buzz is a children's game. So the children start counting If the number is, they sequentially compute 1, 2, 3, 4, 5, 6 like that. If the number is divisible by 3, you say fizz. If the number is divisible by 5, you say buzz. If the number is divisible by both 3 and 5, you say fizz-buzz. All right. If you make a mistake, then you're out. All right. So it goes something like this: 1, 2, fizz; 4, buzz, buzz; 7, 8, fizz, buzz; 11, fizz; 13, 14, buzz. Like, I should have said fizz buzz, right? 15 is, is fizz buzz, right? So that's the game. So the problem now is, as a computer scientist or a programmer, your job is to write a program that can play fizzbuzz, right? The input is, I give you a number, and it should be able to output either the number, like 7 is 7, whereas 9 is a fizz, and 10 is a buzz, like that, right? So the output is either the number itself, whatever input you gave me. If I say 17, the answer is 17. If I gave 18, the answer you would say is fizz. If I gave you 20, you would say buzz. So the program has 4 outputs: the number, fizz, or buzz, or fizz buzz, right? Both. So the input is a number, output is one of 4 possible values. So you need to write a program to do that. Of course, a deep learning solution to the problem would be, you write a program that takes, let's say, a binary version of the input, a certain number of bits to represent whether it's 18 or 20 or 36 or whatever. And the output is one of 4 possible values. So you'd use a scheme which outputs 4 possible discrete values, right? How do you do that in neural networks to get a discrete set of values? By using softmax, right? You use softmax to output one of 4 values, and you'd have a probability. Is it fizz or buzz or fizz buzz, or is it a number? With a certain probability for each of those. It would learn. So I would give a whole bunch of numbers as input and show you. Let's assume it's a supervised learning problem where I present a data set of a set of inputs, and it's got all these outputs. And the job of the machine learning program is to learn to map this. And if I have enough number of samples, enough number of epochs, and the training set is large, it learns to do this and outputs reasonably. And as in any neural network, this is not going to be an absolutely perfect program. It's a machine learning program to map input to output. So you might say, well, in the beginning, it's not going to be very accurate, and then you can keep on training more and more epochs, and on the testing set, it's going to eventually reach 99.8% or something. So whenever you give an input, like, I'd say 173 is the input, it's got to be able to say, is it fizz or fizz buzz, right? But it's not going to be exactly, right, like any machine learning program. It's going to have some small probability of error. Now let's see, if you were to solve this problem using conventional symbolic logic. In a lot of the computer science courses you took as an undergrad or introductory graduate student, if I asked you to write a program for FizzBuzz, you would know exactly how to do that. You would write it using C or C++ or Java or whatever favorite programming language. You would write a logic that has got a definition for a variable X as input, And then you would use some convenient function that is available, such as x modulo 3. X modulo 3 gives an output of what is the remainder after dividing by 3. And if the x modulo 3 is equal to 0, the output would be fizz. And you would check x modulo 5, the output would be buzz. And if x modulo 3 times 5, I suppose, is 15, you would output fizz-buzz. So actually, you would order this logic in a better way. The first thing you would check for is actually fizz-buzz. Okay, if it is divisible by both 3 and 5, if the remainder is 0, then you'd say it's fizz-buzz. If not, you would try the fizz. If not, you would try the buzz. If modulo is not 0 in all these 3 cases, then you say it's some number like 17. It's not divisible by 3 or 5. You would say, well, output acts as your input. Output is y. So you would write a symbolic logical program like that, which is a conventional logic. It's got variables, it's got operations such as x modulo 3, x modulo 5, some operation, built-in operation, and it has got output. So it's got variables, instantiation to the particular value. X takes on the value now 173. And so these are all conventional concepts of symbolic logic, symbolic reasoning. And that program hopefully will be perfect. Given another huge number, 1,782 or something like that, it will be checking for divisible by 15, by 5, and 3, and it outputs the correct value. Whereas my machine learning program, which would learn, seeing what is the association going on here, does a pretty good job, pretty impressive job. It learns based on examples, as if somebody was listening to the children playing the game, but that person has not been told what the rules are, divisible by 3. He's just observing. Whenever 9 comes up, they say buzz or fizz. Whenever 25 comes up, they're saying buzz. So it's as if that person has to learn what kind of a logic these children are following, right? So you see, there are 2 styles of problem solving here. There is the machine learning, maybe even a deep learning program. It's multiple hidden layers that is trying to solve the fizz-buzz problem. And then there is this standard logical solution to the problem. The logical solution to the problem has embedded in it the exact logic that is needed to solve the problem. The machine learning program, nobody sat and wrote that code. It was a machine learning program. It just had input, output, input, output, input, output pairs. And it is trying to figure out what are the values of the hidden units and what is the mapping here, and the weights associated with all the inputs. I'm assuming the input, like, we would have like a 10-bit input, and 173 would be encoded as a 10-bit input coming in, and the output is just one output with 4 possible values. And there would be a hidden layer that is doing the mapping. So we have 2 approaches here. So which is better? Is the neural network approach better, or is the logic-based approach better, is the first question. And one can argue that, hey, the neural network approach is great. I didn't have to figure it out. I didn't need to figure out that it is modulo 3. I don't know what modulo, I've forgotten. Modulo 3, modulo 5. And should it be modulo 15 first, or modulo 3 first, and so on. All that logic I had to figure out and encode it. That is manual labor. And the logic, once the program is written, if somebody else were to look at it and were to find out there's some problem here, let me fix it, there would be some entangled code there. They'd have to work through it using the comments and so on. Why are you doing this here? So on. And so it's a bit of a mess to work with, particularly a long program. And whereas the machine learning one is a simple one, it just takes inputs and outputs and figures out what to do and so on, but it's not giving a perfect answer. So there is one issue. Now let me let me jump directly to Kahneman. This guy Kahneman, right? Kahneman says the human brain has two systems in it, system one and system two. System one is the neural network. System two is deliberative, logical thinking. So he argues that human beings have two processes running, not just one. It's not just one neural network. So think about it. A lot of the things we do, we simply do very routinely. We don't think about it. When you see a friend, you are able to recognize this person immediately. You don't need to have some logical reasoning going on as to, who's this person, what color of hair, or so on. It is just right away. A neural network is doing that job. Or when you're driving a car, right? The car seems to know where to go. You are not even thinking because you're going from home to the office or to school. And that type of thinking is system one. We don't even think about it. And while we're driving, we might be thinking about other things. Only thing is, the other things, of course, may be complicated things. What am I going to do about this or that, and so on. Somewhat deliberative thinking going on there simultaneously. But there is one part which is system one operating, another part is system two operating. And they have done some experiments. After all, Daniel Kahneman won the Nobel Prize. This is his main theory about system one and system two. That 95% of the brain, human brain we're talking about, or I don't know about animal brain. Animal brain may be largely system one. Human brain is, even human beings, 95% is system one. It is a neural network that is doing the recognition or figuring out whether the steering wheel has to be turned left or right, all done very, very quickly without a second thought given to it. And so that's the nature of system one. But 5% of what we do is actually done by the deliberative process, which you can say it's the symbolic reasoning part. And so in everyday problems also, when I ask you what is 2 plus 2, you would say 4. It's probably done immediately by your system one. You don't need to do any more mathematics when I ask you what is 2 plus 2 or 2 plus 3 or 2 plus 7. But if I ask you what is 17 times 24, try that. 17 times 24, how much is that? Well, for that, you cannot answer that question by using system one, saying, do I know the answer right away? Can you tell me? You have to say, no, I have to work this out. 17 times 24. Some logic I have to apply. Maybe make it 20 times 24, and that gives you 480. And no, it's not quite 20, 17 times. It's got to be smaller than that. Maybe 3 times 24 and subtract that. Anyway, some kind of symbolic reasoning, symbolic logic is needed to solve a more complicated problem. So Kahneman's theory is that he says the brain is not divided into two parts. This part is doing the neural network, and this part is doing the deliberative thinking. He says it goes on simultaneously. But he gives in his book many, many examples of system one and system two. And in every situation you can think of, there are these kinds of things in language, in mathematics, in our constant day-to-day routine problems and so on. Uh, that is the nature of things. And he went on to show how businesses and all also do this in some extent and so on. And so it's somehow related to economics also, which is why he won the Nobel Prize for that. But it seems to have relevance. So how is it relevant to us? And so we can say, look, neural networks are pretty good. Deep learning is pretty good, almost human-like. But we say almost. When I ask you, can you write a neural network to do fizz-buzz? Some of you wrote the code, in 574. If you want to do a small project, here is what I'm going to suggest to you: is look at your fizz-buzz machine learning code, and then there is the logical code for the same problem. The nice thing about the logical code is you can generate an explanation as to why did you say it is fizz buzz, or why did you say it's fizz, why did you say it's buzz. You can generate an answer saying modulo 0, modulo 0. That's the explanation. If you ask the machine learning program, why did you say fizz buzz or fizz, it, it will point to the hidden unit values. That's what it caused it. And it doesn't even get it perfectly. So people implemented it and found that there is only so much accuracy in this program. So if you implement it, try it out. Increase the number of hidden units and maybe increase the number of layers. Try it out. You're going to get a pretty good program, machine learning program, 99.9% or something like that. But still, some cases, even a simple example that I came across, when you input 100, it got it as fizz. It didn't do fizz buzz on it. Oh, it is fizz, right? Yeah. 100 is fizz. Okay. So now some other example that doesn't get it quite right. So even simple problem, fizz buzz. Another example is, identity function. Let's say the program you input for an input 0000, 4-bit input. The output is 0000. What for 0? You got a 0 output. Well, okay. How about 0010? Output is 0010. Okay. For 0010, I should output 0010. And then I say, okay, how about let's go from 0 to, let's go to 4. So let's say 0100. Output is 0100. Oh, okay. Fine. I learned how to do that. And then I go to maybe 6, all right? 0110. Output is 0110. I'm seeing a pattern in your data you're giving me. The output is the same as the input. It's like a, what do you call it? Autoencoder, right? Output and input are one and the same. So, okay. It's the function you're trying to implement looks like the identity function. And then you keep on inputting. Let's say we just gave it even numbers and it keeps on doing it perfectly. That kind of even numbers, it handles it. But then you input now an odd number into the system, like 0001. Well, now the peculiar thing is it will make a mistake. It will make a mistake on the input you gave. A human being would have directly understood that the kind of examples you are giving me, the input output, they're all the same. Very quickly we see that. And whereas a program is looking for all these bit combinations and things like that, and is unable to learn that this is the exact identity function that is what you're trying to teach me. Maybe it's going to get it right a lot of the time, and it's going to fail on some of these other cases. So these are some of the issues about deep learning and conventional logical reasoning. One more example. Those of you who are familiar with NLP, I think Archita would know this. She knows more about NLP than I do. She's been implementing GPT and all these things. You know, there was GPT-2. GPT-3 is just trained with a lot more stuff. GPT-2 was considered quite a revolution. And you can input into GPT-2 an input sentence and ask it to complete it. So for example, if you say, the cat sat on the, what is the next word? The cat sat on the. If you give it such an input to GPT-2, it will say, well, the choices for the next word are the cat sat on the mat, maybe. Mat is the top choice, and cat sat on the floor, or cat sat on the bed, or the cat sat on the couch, or cat sat on the window. There's so many other possibilities, but maybe the top choice is cat sat on the mat. It's able to do that a pretty good job. Saying cat sat on the mat, it answers that question. And so, you know, they showed some spectacular achievements of GPT-2, all based on deep learning. And this was something about explorers found, this is a sentence you input to GPT-2. Explorers found that in the Andes Mountains in South America, they found a group of unicorns. They found, unicorn is a horse with a horn. No such thing exists. So a group of researchers found a set of unicorns, and the team was led by a South American research scientist. And they kind of give a sentence like that as input to GPT-2. And then ask GPT-2 to predict what is the next, not word, but next sentence or next paragraph. Well, GPT-2 is pretty creative, Unicorns don't exist, but it continues the story and says, these unicorns spoke perfect English. And the leader of the team, his name, they even given a name, Jose Martinez, was so thrilled that they found it and they reported it to the Argentine government and so on and so forth. It kind of gives you a fascinating output. GPT-2 is very imaginative. It's like a good storyteller. You prompt them with one sentence and their imagination takes over and they can tell you a beautiful story based on that one sentence. Maybe some of you are able to do that yourselves, right? So GPT-2 is like that. Well, say, look at this. Amazing how well GPT-2 works, that it can generate all these human-like sentences and paragraphs, and it can write articles, it can write fake news articles and all that. And when one of the companies that produced this software, I think the OpenAI company, they said, we're not going to release the software, we are not going to release the code because it's so good that you can use it to generate all kinds of nonsense, which looks very plausible and logical. Okay. But, try out some other example. For example, they tried out, I went to the laundry and dropped off my clothes at my, no, I think it goes like this. I dropped off my clothes at my mother's house. And then I asked the question, where are my clothes? And, I don't know the exact sentence, something to that effect. And the answer came out as, okay, what did you say? You dropped off your clothes. Okay. It says, where are my clothes? It can say your clothes are at the laundry. Okay. You said you dropped off your clothes at your mother's house, and now you're asking where are the clothes and saying it's at the laundry. Why does it give an answer like that? Is it did not do some reasoning here, because based on all the learning it has done, when you say you dropped off your clothes, it's not common that you drop off your clothes at your mother's house. It's more common that you drop it off at the laundry. And so it gave such an answer, not figuring out the logic of what was said. Maybe that was a bad example. Or you give some other example, which say things like, I have 3 cups. Now I go and get 3 more cups. And then you ask the question, how many cups do I have? It comes back and says 17. So what? I just told you I have 3 cups and I got 3 more cups. And you are answering it as 17. Did not do the logic of adding the 3 and 3 in the sentences that came earlier. How did it say 17? It was based on a large repertoire of language, and it had learned from, and what kind of scenarios. So it is kind of looking at the surface level of a lot of sentences, right? So what I'm pointing out here is GPT-2 is very impressive. Fizzbuzz was also very impressive. Identity function was impressive. But when it comes to some kind of reasoning that has to go on, it falls short and gives you nonsensical answers. So one can argue that these deep learning programs, while they are extremely impressive, can they be trusted? Particularly in scenarios you have not seen before. Will they just give you a nonsensical answer? It's driving a spacecraft or something like that, where you encounter a scenario you've not seen before. Can you trust it to reason through? So deep learning is a bit like system one, works extremely, extremely well under normal circumstances, simple arithmetic. But when I ask you to do in your head 17 times 24, so okay, I got to turn to reasoning. I can't simply give you an answer off the top of my head. I need to work this out. So what Kahneman is saying about the brain, based on his observations, is something that may be very relevant to the implementation of AI. And so one more thing Kahneman says is that we may have 2 systems that are operating. Whenever we're doing anything, we have one system operating, and we have another system when we need it, right? We call the other system, okay, this cannot be solved by system 1. It's got to be done by system 2, which is more logical, conventional program. So let's take a look at the Fizzbuzz program. So what Kahneman is also saying is, if you start encountering these kinds of problems, like system 2 level problems, quite often, right? There is some combination of things. So you're trying to find your way to some building on campus, and the first time around, you couldn't use system 1. You need to use system 2, logically thinking about where all I should go, which room I should go, which corridor I should take, and all that. But once you have done it, or maybe after you've done it twice or thrice, well, it becomes a standard solution, which you can now push it into system 1. So without thinking, you are going from where you are to the classroom, right? Just like the car driving, in the beginning, when you move to a new place, you have to figure out what is the route. But once you have done it, it is no longer constant reasoning going on. It becomes a solution that can be pushed to the other side. And you also have a fairly good idea of what it is doing. So the question now is, can computer programs be designed like that as well? So, and I'm giving you a very concrete example that you have a machine learning solution to fizz-buzz. You have a symbolic solution to fizz-buzz. But once you have the symbolic solution figured out, can that somehow be encoded and made part of system one? It's going to be an interesting question. How can this solution be encoded so that the program exactly knows that what's going on here is not some kind of a mapping into fizz-buzz and so on, but it is actually going about division by 3, division by 5, and that is the logic that has to be encoded by the program, by the system one program itself. So Kahneman's theory says it's being transferred. So you have solutions on the on the deep learning side of things, and you have solutions on the symbolic side of things. But once you start getting used to the symbolic side of things, you push this over to the other side. That's his hypothesis. So, or the identity function. So the program is learning the identity function. It's finding the mapping, and then, but it starts making mistakes when it gives give you new examples. And how would you transfer that over? All right. So that is the kind of thing. And we have about 10 different research problems we'll discuss in the next session. If you want, you can start looking at 1.2 about what are some research problems here. There are 10 different problem statements there. So we have to be knowledgeable about both parts. This part here, deep learning part, it's all about neural networks and solving the problem well. There's the thinking fast part, and it solves these problems well, but it is not a trustworthy solution. It's not trustworthy because you don't know whether it's going to get the right answer on very peculiar things it has not seen before. Of course, you can say, well, you're not being fair to deep learning, because there is a whole chapter here in this book called regularization, right? I spend a lot of time when I teach deep learning. What is regularization? There are 20 different methods of regularization one can think of. And what is regularization? Well, a simple one is early stopping, that you don't keep on training on the testing set because it can do overfitting, right? Overfitting, so that when I present any new example, it will not do as well. But is overfitting, is exactly fit to the data. It's not learned to generalize. And what do you mean by generalize is to solve the problem to situations you have not encountered before. Well, that's exactly the definition of this regularization here. How do you get it to perform on situations you have not seen before? And we are saying that is exactly the problem with machine learning, is it does not generalize well. Well, there are methods of regularization that take you some way. And the hypothesis here is that regularization works only around a cluster of these points. So you've given a test set. A training set. You got these input examples. These are the corresponding outputs. And so around those kinds of points, it learned some generalization. It's not exactly this to this, but maybe a few in some space, that it is some points that are around that it'll do well. But if I give it something far away, it's going to fail in those situations. So that is the criticism here. That is the criticism. And so this is an issue of, we can say, well, try and solve it using very good regularization methods. And so maybe you'll keep doing better. Maybe it'll generalize better and better. But will it ever learn the absolute, correct logic to say, why did you say fizz or why did you say fizz buzz? That type of an explanation. So is it possible somehow to learn this and eventually transfer it off? We are not saying, so deep learning is good for 95% of the world's problems. That's the good news, right? All right, you can use deep learning for every problem that you encounter, but then you're also worried about, when do you switch? Maybe we should just have two systems in parallel. There is the deep learning part, or the system one part, and there is a symbolic part. Deep learning part is based on this book, and the symbolic reasoning part is based on this book. All right. Why do I say it's based on this book? Probabilistic graphical models. Well, this is about probabilistic reasoning. It's about reasoning. You have some input, and you have to reason your way to the output. And the reasoning is all probabilistic. It's the kinds of problems we are interested in machine learning and in AI are not problems where you have an exact solution to the problem. There is some uncertainty associated in solving the problem. And so we want to look at a probabilistic solution. So there is a certain probability. So the outputs are not exactly, 1, 2, and 3, or we say a probability of 1, probability of 2, probability of 3. If the answer is 1, we may have a high probability. So probabilistic reasoning can be done in the conventional reasoning domain. Probabilistic graphical models show you how you can reason from input to output, multiplying probabilities, saying, okay, from this stage, we go to the next stage. But these are all symbolic reasoning steps. For instance, if you say the student got a job offer at this very prestigious, company. So that is the input. Student A got a job offer at a prestigious company. So your inference may be, well, that's, if you don't know anything more about the student, that student must be very smart to be able to get a job at this highly prestigious place. Maybe, I don't know, Google research or something, which might be very prestigious to get a job offer. So you conclude that. And how do you do that? You go through, well, you say the student got a job offer. So if the student has got a job offer, he must have got good recommendation letters. He must have had a good score on some tests and so on. And so if the student has got good recommendations and has a good score, then the student probably is intelligent. So that is how you lead to the conclusion. So the input, a student got a job offer, and the output is, what kind of a student is this? The student, high probability the student is very smart, so on. So that is the kind of reasoning that goes on, and probabilistic graphical models are full of that. The example we have in Daphne Kohler's book is about students and their intelligence and their SAT scores and the recommendation letters and job offers and that kind of thing. So it shows how you can multiply those probabilities to calculate the exact probability of any output. Is the student intelligent or the student is not so intelligent? You can calculate the probability of that based on data sets from which you can learn what are called as conditional probability distributions. Given this, what's the probability of that? And you have to work through these conditional probability tables to do the reasoning. That's what the probabilistic graphical models course or the advanced machine learning course deals with. Here we are saying, let's assume we have a reasonable solution like that. And how do we deal with this? So what I'm thinking is, so we're going to go through this systematically. We're going to do the thinking fast and thinking slow, and what are the different steps in these, and then we will look at some other theories people have put forward, such as robust AI. In robust AI, we talk about how today's AI, which is based on deep learning, is not robust in the sense these kinds of outliers and so on. It fails in these. It is called pointillistic artificial intelligence. It does very well in certain things, but not so well. So we want to point out these things, and then we'll talk about if you have a single system that has got both components. I'm sure those who are in NLP, maybe Arshita would know this. They have found in some of their projects that all the training with the GPT-2 or GPT-3 or BERT or what have you does extremely well, but it breaks down very quickly. They find that the Alexa or whatever device suddenly is unable to handle and gives nonsensical answers like, I dropped off my clothes at my mother's, and where is my laundry? Where are my clothes? It says it's the laundry, that kind of thing, which hasn't done the reasoning part. So how do we do these two things? One can say, well, it's got to have both components. There is the deep learning component, and maybe in parallel there is another component, or in sequence there is another component. So what is the message passing between these two? Is it possible for you to define a problem? This is true probably even Alina, in your area of reinforcement learning also you might find. Actually, reinforcement learning has been bullish on deep learning. It says, well, deep learning is great for reinforcement learning where you have the environment giving you feedback. And I think some of the recent books on Sutton and so on saying, okay, deep learning is amazing and this is what is needed for reinforcement learning. Well, even there you might find that there are some scenarios where this helps. Natural language processing definitely could use symbolic reasoning beyond just feeding. How does GPT-2 work? GPT-2 to GPT-3 was, well, okay, order of magnitude more text. Instead of digesting a billion documents, you go to several billion documents, and you're learning all these possible combinations of words and so on, and you're able to work with all of them, right? And so that has been the brute force learning that has gone on. And how do we now incorporate these things? So when we look at those 10 research problems, so what I want to do is you can start looking at that part. So I still need to go over the lectures here. I'll go over the structure of what we'll cover, and then we'll think of what is it that we could do. Maybe we can at least define these problems. Just take this example of fizz-buzz. How could you convert it into a problem where you can actually try and solve it so that you have the correct solution as well as the approximate solution both available at the same time? Then comes the issue, how do you learn the logical structure? And that becomes an area of learning probabilistic graphical models. So what are the relationship between symbolic variables, and how do we learn the structure of the probabilistic graph? So, so one can talk about not learning about the data, but learning about a probabilistic graph. Can this be done simultaneously? All right. The answers are not clear. So things turn out to be hard-looking problems, but we should take on simple problems, identity function solution or the fizz-buzz problem solution, and see, can we come up with a solution to this problem? And that might give us an insight into what really needs to be done, right? So let me share some things with you now. And I'm going to go to the share screen. And okay, I hope you can see my Neurosymbolic Artificial Intelligence course webpage, right?
Yes.
And you can see it, right?
Yep.
Yeah. Okay, thanks, GRU,
Yeah.
for being alive. Everybody is gone away. All right. So I just put this up. What is all these things here? Uh, Neurosymbolic Artificial Intelligence course. I'm thinking that this seminar can eventually be a course, but it's not quite ready. It's like ideas. I just threw in some sets of slides I already had and said, okay, let us see if we can structure around it. Let's see what I say. Much of today's successful artificial intelligence models are based on deep learning inspired by biological neural networks. Yeah, everything is deep learning today. They're inspired by biological neural networks. They've eclipsed an earlier approach to AI known as knowledge-based systems, in which the world is represented in the form of predetermined symbols with inference based on logic and probabilistic reasoning. Logic was the earlier approach, right? If then else type of statements, or we'd have a logical sequence. The conventional programming. Conventional programming can be enhanced by probabilistic reasoning. So it's not just exact reasoning, it could be probabilistic. If the probabilities are 1 and 0, then it becomes exact. However, the symbolic approach can better address limitations of deep learning, such as adaptability, generalizability, robustness, explainability, abstraction, common sense, causal reasoning. So there are all kinds of things that are done well by symbolic reasoning. And can deep learning be used for that? Actually, there is a school of thought that deep learning becomes deeper learning and so on. Whatever you can do, it can be done by deep learning. There is that line of thought. So that line of thought says waste of time for you to spend on symbolic methods. That is all, old stuff. It's like doing, something, aircraft technology based on old ideas that no longer hold, or physics might be physics based on ether and things like that, which no longer hold. There are better theories available today. And trying to fix it by using old technology is silly. You should really work with the latest and greatest technology of today, which is deep learning. But we've already seen some of the limitations here. It cannot tell you what is fizz-buzz doing, and it cannot tell you even the identity function exactly. Of course, you can counter argue these things, I suppose. And anyway, so the use of both approaches in the same system have cognitive support. Now we are saying a hybrid approach. It's not one or the other, but it's both. It's a hybrid approach, and it has cognitive support. I say cognitive support because Daniel Kahneman was basically a psychologist who got the Nobel Prize in economics, but he is the one who formulated these fast and slow thinking. So we can say that idea can be useful here. Deep learning plays the role of fast thinking, and symbolic approach plays the role of slow thinking, right? When you have not had your coffee in the morning, I suppose in Korea it's 6 a.m. now. You've not had your coffee, then you're using mostly your system 1, right? After you have your coffee, it becomes system 2, right? Okay, anyway, so a lot of it can be done by fast thinking. The seminar course covers cognitive theories of fast and slow thinking, robust artificial intelligence. So today's topic is actually neurosymbolic AI overview. I think I've covered a lot of this material already, given in those slides. I put these slides together to get my thoughts together, but I think I've covered most of those material in my, extempore discussion, which is based on these slides here. And the topic two is research topics on what are some of the things one could do. And then is 1.3 is robust AI. I keep updating these slides. I updated neurosymbolic AI earlier this morning, and I also updated robust AI. Robust AI comes from practitioners of the symbolic old style AI. So what has happened in AI is over the last 5 years or 10 years, slowly all the classical symbolic reasoning methods of AI, which is conventional logic, has been pushed aside, saying we don't need all of this stuff. Everything can be done by deep learning. So now they're coming back. So this robust AI is coming back and saying, hey, look, you got this problem, this problem, this problem with deep learning. And so our methods should still be useful. And to have a trustworthy system, you need to have some of that. So how do we bring that in? So then I threw in some slides here. We don't necessarily have to cover all of it. I just put it in for those who may not have all the background. The probabilistic artificial intelligence, the fourth topic, 1.4, is kind of related to probabilistic reasoning. What is that about? And 1.5 is the first set of lecture slides on deep learning. 1.5 is just about the deep learning book, right? So what is deep learning about? And, I'm assuming that all of you have had exposure to that. And then section 2 is PGM, is probabilistic graphical models. What are probabilistic graphical models? Some variant. We don't need to cover all of that in great depth. And then I go into chapter 3, which is local probabilistic models. The reason I put that in, this all comes from my advanced machine learning lecture slides. I put that in because some of these might be useful, like particularly 3.3, context-specific CPDs, where we're talking about a symbolic structure, like a probabilistic graphical model with many nodes and connections. So you can reason through, there's what are called as causal reasoning. The cause of this is this. And you can go the other way around, right? So you can see explanation type of thing. So the bottom up and top down type of reasonings. And in these models, some of the CPDs, the conditional probability tables and distributions can actually be deep learning neural networks. So one can think of a probabilistic graphical model which has nodes and connections. Nodes have children have children, and so on. And then you're doing reasoning through this network where the reasoning is all probabilistic. And but some of the probability tables that are involved for each node can actually be deep learning neural networks. So that becomes a very natural way of uh, integrating symbolic reasoning with deep learning, right? So you can think of a structure so where you're implementing both parts in a hybrid model. And then I put in this thing section on structure learning in Bayesian networks. How do you get a Bayesian network structure? How do you figure out that the job offer depends on the recommendation letter, the strength of the recommendation letter, and the score on on some tests, right? Grade in the class and the recommendation letter together determine the job offer. And so how do we know which is the parent and which is the child in this graph? So that is an interesting problem in structure learning of a Bayesian network. And then, of course, this can be undirected graphical models also called Markov networks. Those of you who've taken 674 will know what this is. So it is there. I just threw that in, saying that might be relevant to some of you. I mean, if I cover all of this, it becomes a lot of 674 is covered here. That's not my intention. I just threw it in saying that might be useful. In 674, I don't cover these last two parts, causality. I don't get time enough. Causality. How do you determine what causes what? It's a very important scientific issue. And this could be, can you learn the causality from the data so that you can construct a probabilistic graphical model? And so what are some of the issues here? Causal Bayesian networks. So can this be learned? And then this last part, I threw that in because there's a lot of discussion going on about what are called as knowledge graphs. The kind of stuff that Google does, right? When you're Googling some topic, they will give you a nice summary of the topic for you on the right-hand side, right? It's you're Googling for a president, and it'll give you on the right-hand side all kinds of details about the president, who the previous presidents were, and so on. It is giving you all kinds of relationships that might be useful for you, called a knowledge graph. And so how do we work on these knowledge graphs? So knowledge graphs may be relevant to these neural and symbolic AI. So this is some of the stuff that might be relevant. Okay, so I may go over this causality and knowledge graphs a bit more than some of these in-between topics, which are largely probabilistic graphical models topics. But that if we don't stumble across much richer material coming along, I have about 3 papers I've listed in UB Learns, and you could you could look at that part, So I'll let you look at that. I think everybody has access to UB Learns here. So okay. So anyway, where was I here? Okay, so let's see, how are we doing on time here? We have okay, we have just done about an hour and a half. Let me run through quickly the neurosymbolic AI introduction. I've gone over the course material. I also wanted to show you a few papers. So I'll expect you to dig up a few papers and keep sending it to me. I want you to participate as much as you can to make our course richer. And I'm trying to share something else, and I'm having a bit of trouble. We're already screen share. How do I screen share another document, right? That's the issue. New share. Okay, there is a button right there. New share. Already got it. Yeah, so papers. All right, here are 3 papers that I've listed in the UB Learns. And those of you who don't have access to UB Learns may want to look at these papers. The first one is titled Fast and Slow AI, done by a bunch of computer scientists. And that might be useful. Some of my ideas in slide 1.1 covers that. The second paper is Robust AI. That one is about all these criticisms of current deep learning, and it also makes a proposal. It says the conventional AI also took inputs from the world, and it actually had models of the world, and using the models of the world, it produced outputs. And of course, these models were all created. These are all cognitive models of the world, and they are created, by people saying this is the kind of model. And the argument in robust AI is that these conventional models have to take advantage of today's deep learning methods. So that is the intriguing question. How can we use the idea of variables, of representations of these variables, and then operations on these variables, instantiation of these variables, all the things about conventional programming, how they can be constantly supplemented by the deep learning approach. So that's what that robust AI paper is about. So I'll go over that. So I'm going to kick off things for the first few weeks. This first 1.1 is about fast and slow AI, and then this I have divided into two parts. 1.1 is fast and slow AI, and 1.2 is the research topics that they outline, saying that's worthwhile pursuing. So I'm hoping one of you, each of you would pick up one of those ideas and saying, that sounds interesting. And what is my thinking? What is my solution to this problem? Assuming that you already know about deep learning, you also know conventional programming, right? That's where you came from. So how can I incorporate both and not say just replace one by the other? And then there is another paper I came across titled Neurosymbolic AI, exactly the topic, but it didn't seem that substantive to me so far. But I haven't really, prepared my lecture on that. I'm going to try to do that after I finish this robust AI. And so now you might come across several papers. So here is one on NLP, on neurosymbolic AI. Pass it along to me, and I will try and cover it if it looks really exciting. And or I might ask you to teach us about it. What are they saying there? So we are in this domain we that nobody knows. This is the approach to neurosymbolic AI. We're just saying there's neural networks, there is symbolic AI. Combine the two, it becomes neurosymbolic AI. Neuro is system one, symbolic is system two. So it's system one and system two. That is what Kahneman is saying. So we have all these very simple underlying things. And that's what we're talking about. Okay. All right. Then let me just quickly go through in maybe, not more than half an hour, the first set of slides. Okay, neurosymbolic AI. So this should run fast. I think I've covered all this material so I can speak faster. Okay. All right. My first slide is this: Foundations of Neurosymbolic AI. The deep learning textbook by Goodfellow, Bengio, and Kurbel. All right, it's 775 pages long. It's got lots of material there about architectures, about regularization. How do you make the neural network, perform things that it had never seen before? And that's called regularization. Optimization is how do we figure out the weights, right, based on their loss function and all that, and applications to various domains and autoencoders and all kinds of topics in deep learning. And then probabilistic graphical models, 1,232 pages. It's all about reasoning in a graph, and the graph may have variables and conditional probability distributions, parents and children, and so on. Given this, so there are conditional probability distributions. Now, do you multiply conditional probability distributions to get the probability of any given value you're looking for? So that is a very, very substantial, deep book on probabilistic graphical models, principles, and techniques. And this one that is on the underlying principle of system one and system two. Again, a 500-page book. And so the topics I have here is actually paradigms of AI, which is just the two topics of deep and symbolic. Causal reasoning comes from symbolic, and deep learning is about is about the fast learning. Kahneman's thinking fast and thinking slow, system 1 and system 2 characteristics, and some experimental justification for that. Software 1.0 and software 2.0, I've usually discussed it in the beginning of the deep learning course I teach, saying, this Tesla, right? Their AI chief there, he says, well, I'm managing two types of software in my lab when they design software for their electric cars, right? And so he's got two types of software. One software written by human beings called software 1.0, and another software written, generated by machine learning programs that have been given examples. And nobody can go and debug that code or anything like that. It's just learned by machine learning, bunch of weights. So in a way, the Tesla car has two types of systems. System one in this case is actually the slow one. That is the old type of software. And then software 2.0 would be the new machine learning software. They're both of those. So the cars are being driven by both. Probably not much connection between the two. So the two paradigms of AI is the deep learning part, which is input, simple features, additional layers, mapping from features to output. Deep learning is a many, many layers like this. Causal layers are input to output with a hand-designed program here. This is a standard, approach to writing code. Of course, causal reasoning, we're saying some kind of input, and the reasoning goes about saying what caused that particular image. It's got to be this, would be the output. What is the cause of it? This is the example that is from the PGM book, from Daphne Kohler's book, of difficulty and intelligence and grade and SAT and letter and applied job. It says to receive a job offer, there is some influence on the letter written and the SAT score. I suppose this is for a bachelor's degree holder. And given the various possible, the letter can have strong or weak, L0, L1. And the SAT score can be S0 and S1, strong or weak. And so there are now 8. This takes on two possibilities. Letter takes on. There's also apply. Did you apply for the job or not? So there are 2 times 2 times 2. That's 8 possibilities of letter, apply, and SAT. And then for every combination of values, you have job offer or not. So for each of the combinations, you have these values. And so this is what's called as a CPD, conditional probability distribution. And like that, there is a relationship between the letter that the student gets from the professor and the grade that the student got in the course. There's some influence. The grade that the student gets in the course is influenced by the difficulty of the course and the intelligence of the student. So there are probability distributions. CPD is associated with grade, with letter, with job. Then we ask the question, if you observe that the student received a job, what's the probability that the student is intelligent? You'll have to multiply these probabilities appropriately, like probability of I equal to 1, intelligence equal to 1, given J equal to 1, job equal to 1, has to be reasoned through all of this and say the probability the student is intelligent given the student got a job offer is 0.619, 61% probability. And that is the reasoning, inference part of it. So just like we have in machine learning, we learn the parameters, and in the field when we apply it, it will tell us what is the value of the output. That's process called inference. There's learning and there's inference. Just like that in the PGM, these probability tables are learned during the learning phase. Some of it is pretty trivial to figure out how often this happens. That's how you fill the tables. That's the learning part. Inference part is to multiply these probabilities appropriately, like this. It's not a trivial part. Inference is NP complete problem actually. So you see, when I say 17 times 24, tell me what is the answer. We are kind of verging into problems that are NP complete and all that. That's inference, right? I mean, you got to work it out. Some of the problems are hard enough that it doesn't have a good solution at all. So, the inference is pretty fast in a deep learning network. Whereas on the other side can be extremely hard. So we are dealing with two of them simultaneously. So how are we going to deal with it? And so the deep learning part is about neural networks and learning and depth. Neural networks are inspired by neural networks of the brain, right? Say, well, our hardware looks like a neural network. It's a whole bunch of neurons and connected to each other and learning the weights. Isn't that how we work? And we say learning is the machines to discover useful. Yeah, we learn representation, saying what are all the values of the hidden layers, and then depth. How many layers should be there? Should there be? And the composition of learned features. So these learned features and features and features. That's what deep learning is about. And deep learning is done using backpropagation. This is a convolutional neural network. This is a variational autoencoder, and this is the gradient space where we have a loss function defined in terms of weights W1 and W2, and we apply gradient descent and doing this efficiently, gradient descent to figure out WT plus 1 equal to WT. All this is done efficiently by backpropagation. The argument that the symbolic side puts forward is this is not enough, that the backprop is not enough, that you need to somehow do other types of learning. What other types? So, well, we can look at learning these graphs and things like that. What kind of algorithms are there to learn graphs? Maybe that is got to coexist. So there is system one learning, system two learning. After system two has been learned, maybe the graph is given, then we somehow map that on. So can you take the logical program and convert it into a neural network? That would be a very nice exercise. Uh, so the current status of AI, so you can say, where is AI today? Human capability is still lacking in AI. What is lacking? Adaptability, I guess, change to a slightly different problem. Generalizability, very different looking input than what it was shown earlier on. Robustness is not completely going off the mark. Explainability, can you tell why did you say 173 is what a fizz or a buzz? Instead of saying that's based on the hidden values being this and this, it's simply saying was it divisible by 3 or 5? Abstraction, can you simplify? Maybe deep learning can do. Common sense. This is something that the symbolic people have tried for long to try and capture what is meant by common sense. I dropped off my clothes at my mother's, and where are my clothes? Well, it will be the mother's house rather than in the laundry. So we know these things as common sense. Causal reasoning. It is, I say it is so because this, because this, because this. And current research addresses these. A lot of deep learning is trying to solve these exact problems. There's a lot of people working on deep learning for explainability and so on. But can we do without the symbolic reasoning? And that has to be incorporated. So the research goal is, can we embed the causal components? Complex and seamless integration of learning and reasoning supported by both implicit and explicit knowledge. And debate is whether end-to-end deep learning can achieve this goal, or whether we need to integrate machine learning with symbolic and logic-based AI techniques. So this is saying, can you solve these problems just using deep learning? You do this deep learning, you that deep learning, maybe the deep learning together will solve the problem. Or and the integration route is most promising. Should we incorporate all this stuff over many, many years? Actually, if you think of all the software that we use, right? The browsers that we use, the apps that we use, right? On our phone, we have all these apps, and then the browsers on the web and so on. They are all based on conventional logic, right? I mean, that's all conventional coding. And maybe some of the newer apps, maybe machine learning, but largely they've been based on conventional logic. Even neural network implementations use conventional logic in their implementations. So, so all of this knowledge about conventional logic, cannot be a waste. Cannot say all of this stuff. Maybe that is only needed for 5% of all thinking, but still it is needed for that 5%. All right. What are some of the deep thinkers are saying about it? Necessary to generalize from raw data to a conscious stream of a few concepts sparsely related to each other. So Bengio is one of the authors of this book, says just don't work with raw data to output, raw data to a consciousness stream to a few concepts. So you want to go from them to a few concepts sparsely related to each other. Let's see another one. Explicit knowledge, symbols, and reasoning should be used to improve the robustness of current AI systems. So explicit knowledge, that is the knowledge that people have been coding and putting in. Symbols and reasoning. Reasoning is the probabilistic graphical model part. Symbols are what are all these variables? And building hybrid systems that use both deep learning and symbolic reasoning techniques. All right, hybrid systems. So we have to see what are these hybrid systems that use both deep learning and symbolic reasoning, employing neurosymbolic AI approach. The paper of 2019. There's got to be more stuff now. So the cognitive approach, comprehension of how humans have evolved to obtain these advanced capabilities can inspire innovative ways to imbue AI systems with these competencies. All right. So humans have evolved to obtain these advanced capabilities. So you can say, look, we are also neural networks in our brain, but then we have evolved to develop these kinds of capabilities. Study and exploit cognitive theories of human reasoning and decision making as a source of inspiration for the causal source of these capabilities. So it says being inspired by the cognitive approach, which is what I picked up on this system 1 and system 2. So Kahneman's theory. This is the guy Kahneman. He's the guy who wrote the book Thinking Fast, Thinking Slow. I think it's Princeton. He's a Nobel laureate there. Human decisions are supported and guided by the cooperation of two main kinds of capabilities. This is what he said. System 1 is thinking fast, provides tools for intuitive, imprecise, fast, and often unconscious decisions. So very quickly, you are getting an answer for everything. All right. So they're mostly reasonable. And thinking slow handles more complex situations where logical and rational thinking is needed to reach a complex decision. So this stuff has been around for a while, Kahneman's ideas. Summaries of the two systems. So the conscious brain has a fast brain over here, which is showing like the hare and the tortoise, right? The rabbit or the hare moves fast. And then the green part here is the slow brain. Maybe our human brain is like that, right? It is in this part, thalamus or something like that, it does things very quickly. And then more slow thinking is done over here, conscious brain. System 1 is fast, system 2 is slow, in the sense it moves in seconds. System 2 may be like a calendar in days. System 1 is unconscious, not aware. System 2 is conscious. All right. So while sleeping also, that's what Z's are here. Unconscious and this is conscious. And this is automatic. All right. Something like a machine running here. Effortful, one to the next to the next. Everyday decisions are system 1, like going to the grocery store and getting a cart and doing your shopping, and system 1 may be enough for doing that. System 2 is complex decisions, some graph here in terms of your investment portfolio and whatnot. System 1 is error prone, and system 2 is reliable. Because you've thought out each step, it's a reliable system, and this can give you wrong answers here. Anyway, I've given some references where I found this. I was just searching on this topic. There's a lot of material on it. So system 1 characteristics, guided mainly by intuition, not deliberation. And fast answers to very simple questions. And answers are sometimes wrong due to unconscious bias or reliance on heuristics. Bias can creep in here. System 1 is quickly making the decision. It might be wrong. It might have bias built in. And system 1 usually do not have an explanation. How did you gauge that this situation is dangerous or whatever? You don't have an explanation. Able to build models of the world, although inaccurate, imprecise, can fill knowledge gaps through causal inference, allow us to respond well to many stimuli of our everyday life. So we are able to build these models very, very quickly. And so everyday life is based on system 1, the fast thinking. For examples of system 1 task, finding the answer to a very simple arithmetic calculation, 2 plus 2. All right. And reaching out to grab something that is going to fall. Right? We reach out quickly, something is going to fall off the table. We use our system 1 about 95% of the time when we need to make a decision. So most decisions are system 1. Role of system 2, when the problem is too complex for system 1, system 2 kicks in and solves it with access to additional computational resources, full attention, and sophisticated logical reasoning. Right? I think we can all agree that we do this all the time. A lot of the time, system 1 is enough. But if we have to focus on something, like an exam or something, system 2 kicks in and solves it with access to additional computational resources, full attention, sophisticated logical reasoning. So example of system 2 task, solving a complex arithmetic calculation or a multi-criteria optimization problem. To do this, humans need to be able to recognize that a problem goes beyond a threshold of cognitive ease, and therefore the need to activate a more global and accurate reasoning machinery. Hence, introspection is essential in this process. Isn't that interesting? If you have a deep learning system for a problem, can it come to a point and say, hey, look, I can't really tell. I'm going to pass this along to system 2, which is already available in the system. That would be interesting architecture, wouldn't it? Where whatever the problem you're trying to solve, maybe it is for the problem of image recognition, right? You can say, look, most of the time I can recognize who it is. There are some difficult problems I have to think about it. So I need to pass it along to a more deliberative process. That would be an example of building a system 1, system 2 system. When is system 2 invoked? A new or difficult problem is handled by system 2, and certain problems over time pass on to system 1. Okay. So system 2, after some time, says, okay, I know how to solve this problem. It can be done quickly. Procedures used by system 2 are used to accumulate examples that system 1 can later use readily with little effort. So all these become learning examples. Problems initially solvable only by system 2 reasoning tools can become manageable by system 1. Example, reading text in our own native language. All right. So we do reading text. In the beginning, we are learning how to, a child learns, ABCs and all that, right? It takes some effort to figure it out. But then that gets passed on quickly to system 1, saying, okay, we don't need to think about it. The child has to think about it to learn it. So, however, that does not happen with all tasks. Finding correct solution to complex arithmetic, all right? It's with all tasks. Well, okay, I've solved 17 times 24. Can I pass it along to system 1? Complex arithmetic, right? Maybe not. A lot of problems, it can be done, and sometimes it is. And then the problem is system 2 is supported by system 1. System 2 does not usually work by itself. System 2 needs help of system 1 too, supported by system 1 in its elaborate calculations, right? So 17 times 24, we might be doing some simpler steps that are all done by system 1. When searching for a solution in a very large solution space, system 2 does not usually explore the whole search space, but may employ heuristics that are provided by system 1 and that help in focusing the attention only on the most promising parts of the space. This allows system 2 to work with manageable time and space. So we use it maybe sparingly. Data level causality by system 1. System 1 is also capable of basic causal reasoning. You can say, well, this is because of that. Allows it to build a possibly imprecise and biased model of the world, even it has incomplete knowledge, and to use it to tackle simple tasks. System 1 data level causality skills support more complex, accurate reasoning of system 2 on more complex problems. So there is some level of causality in system 1, and that can be also worked with in system 2 on causality. Why the why type of answer? Why did you give that answer? Multitasking by system 1. System 1 reasoning at various levels of abstraction, right? That's what deep learning is all about, various levels of abstraction. Adapt to new environments. Can be used to adapt a new environment. Generalize from experience to other problems and easily multitask. So system 1 reasoning has all these advantages that we can learn in something. It's called transfer learning, right? We've got a chapter on transfer learning and deep learning. How can we go from one problem to another problem? Recognizing, insects after you have a program to do recognizing animals. And most of the features and all that can be useful. System 2 is sequential, requires full attention to devise, execute appropriate procedure for complex or new problem. Only one complex task at a time is handled. So system 2, the slow deliberative process, is only solves one problem at a time. System 1 works at a local level, activates only a specific part of the brain. Example, recognize a familiar face or when we speak, right? So at a local level, we can recognize a face or when we speak, specific part of the brain. System 2 involves more regions of the brain, combines contributions, works at a global level. So, all right, we know that certain tasks very quickly we do, certain other tasks we have to think about it. Multiple specialized agents, components, skills supports the functioning of both systems, not as multi-agent architecture terminology, but as metaphors for two broad classes of information processing. So do we need a multi-agent architecture? So one is doing this and the other one is doing that. The same brain is doing both. So it's not that it's completely divided up. Anyway, these are all observations, stories and abstractions. Now we're talking about evolution here. Success of Homo sapiens, human beings over other primates, right? Monkeys. Ability to abstract high-level stories. We're able to abstract something. Yeah, what makes human beings more successful than other animals, including, monkeys and chimpanzees and so on? Our ability to abstract high-level stories, allow collaboration with others at scale, does have a broader impact influence. So people working on evolution have said, what is it that made human beings more successful is we can abstract higher level descriptions, share with others, saying this is what happened, and allows us to collaborate and so do larger things. Abstracting concepts is necessary for stories. To be able to say what is that experience is higher level concepts. And conscious decision beyond involuntary reaction, right? So we are consciously deciding things, whereas an animal will be doing involuntary reaction, right? It knows involuntary to look for food and so on. To abstract, generalize, and reason about scenarios and concepts that do not physically exist. So we can do that. Scenarios, we can follow a story even though physically it doesn't exist. To focus attention to certain limited set of features and process them in depth while disregarding others. So these are all the things. So you see, what it is saying is this is what intelligence is. Can deep learning do all of this, or do we need some kind of another reasoning to add to it? Questions being asked, that's what's being asked here, not full answers. Okay, this gets into some very interesting stuff, experimental justification. This gets into psychology type of work, two forms of consciousness. We have I consciousness called information consciousness, which is related to system 2. And then M for mystery consciousness related to system 1. So mystery is this neural network, you can think of it as a mystery, right? You can't explain how it's working. It's able to do it. Whereas the system 2 is information consciousness. We're saying we do this because this is the logic and so on. So we have that is information, information is being passed along. One is information, the other one mystery. Mystery, you can think of it as system 1, and information is system 2. Information consciousness, that is the system 2, is the ability to solve possibly complex problems by recognizing necessary processing steps in specific, even new context to tackle a desired problem. And this I consciousness is related to system 2's high fidelity processing mode, considering a problem and harnessing the relevant faculties of our cognition to devise a plan to solve it. So it is saying there are two types of consciousness going on here. One just going along with system, in this case, system 2 we're talking about first. Mystery consciousness, system 1, ability to build a simplified, approximate, and subjective model of people's, both ourselves and others, mind, beliefs, and intentions. And such low fidelity model building can be linked to system 1 System 1 is able to form a rapid but usually inexact model of the world. Right? See, we're just talking about the psychologist's point of view, Kahnemann's point of view. This is what they're observing. Not that there is a computational analog for every detail here, but it's very interesting for us to observe it before we think, hey, deep learning is going to solve the world. Before saying that, think about all the things that needs to be done. Humans excel at eye consciousness. This is our strength. We can do system 2. While many animals and primates possess various levels of M consciousness, animals also, they're even better than human beings, right? A dog can recognize people and danger, smell, so much better than human beings. That's all based on M consciousness. But for eye consciousness, humans excel at eye consciousness. M consciousness can even sustain in presence of limited eye consciousness. So yet a sophisticated eye consciousness needs to rely on M consciousness. So a sophisticated eye consciousness, a person who can very quickly solve complicated problems, still has to use some M consciousness. And M consciousness can even sustain in presence of limited. Yeah, even without much eye consciousness, M consciousness may be enough. But sophisticated eye consciousness needs M consciousness. Without a model of the mind, it's difficult to devise how to adapt to new environments and solve complex problems. Okay, this part is a takeoff on the software 1 and software 2 I mentioned, right? Software developer, software 1 is classical stack. See, there are all these streams of ideas coming in here. We got the psychologists talking about system 1 and system 2. We've got deep learning and probabilistic graphical model courses that you've taken. And we talked to the Tesla chief of software, and he says, I got 2 types of code in my lab here. I got software 1.0 classical stack, which is Linux and Apache and MySQL and Python and Perl. This is what the software 1.2 is made up of. It's a classical stack. It's code written, we write. He says, that is, I call it a software 1.0. And he says, I got this code written by the optimizer, which is all coming out of my using Keras or TensorFlow. And it's in a user-unfriendly language. There are millions of weights, no human involved in coding. It's got all these numbers. This is a neural network code here. There is no human involved in any of this coding. It was just a machine learning program that learned all these weights. And so I got 2 types of things in my lab. So this keeps on appearing again. There's system 1, system 2, software 1, software 2, eye conscious, M consciousness. Psychologists are talking about it. The software developers are talking about it. The AI people now we are saying, yeah, we got a whole bunch of people only believing in deep learning and a bunch of people completely left out saying, what is this? We've been doing all this AI, it's become useless. And so we are all sitting here with all of this stuff. So isn't it time to put them together, right? That's what this part is about. Here is the fizz-buzz I was mentioning. Software 1.0 and software 2.0. Here's the code for software 1.0. Print I equal to 1 through 100, except if divisible by 3, print fizz, if divisible by 5, print buzz, if divisible by both 3 and 5, print fizz buzz. 2 approaches. Here is the C++ code. And this is the Python TensorFlow code. So there are the 2 approaches to the same problem, machine learning approach. And it's got a hidden layer and all that here, right? So Karpathy is the name of the guy who runs the Tesla software. He works for Elon Musk. He's the AI chief for Tesla. So if you hear him talk or one of his blogs, he says benefits of software 2.0. This is his AI machine learning software. It's computationally homogeneous. Sandwich of 2 operations, matrix multiplier ReLU. He says the computation of a neural network is what? Matrix multiplication and then ReLU, right? ReLU is equivalent to the sigmoid and all that kind of thing. So you need a nonlinearity, matrix multiply. That could be CNN. That's how it works. Simple to bake into silicon. This can be easily done in hardware, let alone software. Small instruction set, constant runtime. Every iteration for forward pass, the same floating point operations, constant memory use, highly portable. Sequence of matrix multiplies is easier, very agile. If you write a conventional code in C++, it is hard to speed up. Instead, remove half of channels. If you want to speed up, remove half the channels in the neural network. Can meld into optimal whole. Software often as modules can jointly optimize. And saying it's better than you. Saying, why should you use machine learning? You were saying it's better than you. All right. So that's what I got on this topic. All right. Summary. I think I've summarized all of this. I don't have that slide. So we come to the end then. Is we have talked about these two streams of thought. And our goal in this seminar is to see how this can be realized rather than simply being ideas. And this is why next lecture will be on the 10 research topics of neurosymbolic AI. You may want to look at it ahead of time. And I'm also just suggesting taking on some simple thing like learning an identity function. Can you do it by machine learning? Can you do it by conventional logic? And how do we meld the two so that you can move from one to the other? How do we hand off from one to the other? So many interesting questions here. So I've driven home the point by saying there is a need for this, by mentioning so many problems that we do only approximately. We are not doing exactly. And to make it trustworthy, maybe it's got to be exact, right? So those are the issues here. All right, I'm going to stop there and take on any questions that any of you might have. All right. Okay. The floor is open. Anybody have any thoughts, comments? All right. Okay, I just have a question. Are there any students here who are not from UB? Not students at UB? If so, send me an email so that I can share the material with you. And, the students at UB have access to UB Learns. The others have my public website that I've shared with you. I try to put in both places, but the UB Learns is a little bit more specific as to which lecture on which day and so on, whereas the other one is more general. Okay. All right. Thank you all. And I hope I opened some thoughts in you in terms of what you could be doing, how you could contribute, or at least bring to my attention some papers that are worth reading. Okay. All right, then. Have a good evening.
Thank you, Professor.
Yeah.
Thank you, sir.